which of these four resonance structures contributes most to the overall picture of this molecule here? Oops, well, I messed it up at the time, right? But, okay, so we want to think, what we want to point out first is these resonance structures. What this problem shows is that these resonance structures, these Lewis structures, are not perfect representations of what a molecule actually is, right? You know, double bonds and stuff, you know, those aren't really real, right? There's like bonds that are almost double, that are a little stronger than double, a little weaker, right? It's all on a continuum. And these electron clouds, right? They're clouds, you know, and these electrons are popping in and out of space, you know, and going through nodes, and you know, it's all very crazy, right? And simplifying it to these line structures, with these bonds and lone pairs of electrons, that's what it does. It just simplifies it, you know, but it's not a perfect representation of these actual molecules. And so resonance tells us that, yeah, okay, we can draw this out, but what we actually have in this molecule is something in between this and its resonance structure, right? Something along that continuum is what's actually going on. And you know, that goes to a whole lot of things. Makes you think about the world all crazy. It's intense. That's why we're going. That's why I'm into it, right? Okay. So, what will contribute the most to the overall picture of this molecule? It'll be the most stable resonance structure. That's the key topic, the key concept here. The more stable a resonance structure it is, the more it contributes to how that molecule actually is and its properties, and right. So basically, go A, B, C, D, see which one is the most stable itself, and it will contribute the most. So we can go through these, and we would be able to show that we can push arrows around this guy and make all of these guys. But let's just look at the stability, because it does work out like that. So we want, first, ideally, when we make resonance, we want to keep octets with all our atoms, besides hydrogen. Right? Keep octets, and we want minus charges, formal charges of negative on more electronegative atoms, and formal positive charge on atoms on less electronegative atoms. Right? So, right away, let's see. So this guy right here we can cross off, just looking through these molecules, scanning over them real quick. This carbon has one bond here, and it's bonded to one H. So it only has 3 bonds, no lone pairs, so it does not meet an octet, means it's very unstable. So look around. Oh, that's got this. Should be 1 bond, right? Otherwise it wouldn't make sense. Okay, so this has 3 bonds again, no lone pairs. D is also not an answer. So in the problem, it is a single bond there, out of the ACS guide. Okay, so we're left with A and C. All these carbons, nitrogens, oxygens meet the octet rule. So what we care about is where the formal charges are at. So we have formal charge minus on an O, plus on a nitrogen, right? In terms of electronegativity, O is more electronegative than N, which is more electronegative than C, right? So here's the opposite. We have a formal charge on C of negative, positive formal charge on N, which it should be the other way around in terms of electronegativity. This has it the right way, so A is our right resonance structure, or our most stable resonance structure, and therefore contributes the most to the overall picture of the molecule.